Somewhere out there, orbiting a distant star, another ocean may be reflecting sunlight across an alien sky. Another coastline may exist beneath unfamiliar clouds. Another world may be circling its star at just the right distance for liquid water to survive. And perhaps, somewhere on that distant world, something is looking back. For as long as humanity has understood that Earth is a planet, one question has refused to disappear. Are we alone? The universe is unimaginably vast. Our galaxy alone contains hundreds of billions of stars. Beyond it lie trillions of other galaxies stretching across the observable cosmos. The numbers are so large that they almost lose meaning. Yet despite this overwhelming scale, we still know of only one planet that definitely hosts life: Earth. It may seem strange that after centuries of astronomy, thousands of satellites, and some of the most advanced observatories ever built, we still haven't found a second living world. But the search is harder than it sounds. Planets do not shine like stars. They hide beside them. A distant planet is often billions of times dimmer than the star it orbits, making direct observation extremely difficult. Trying to photograph one is like attempting to spot a firefly flying beside a lighthouse from thousands of miles away. For decades, astronomers had little choice but to search indirectly. They watched stars carefully, patiently, relentlessly, and eventually, tiny clues began to appear. A star would dim ever so slightly, not enough for the human eye to notice, not enough to stand out immediately, but enough for sensitive instruments to detect. The cause was simple. A planet had passed in front of the star. For a brief moment, it blocked a tiny fraction of its light. Then it moved on, again and again, orbit after orbit. The pattern repeated. A hidden world had revealed itself. Using this method, missions such as the Kepler Space Telescope transformed astronomy forever. Suddenly, planets were no longer rare discoveries. They were everywhere, thousands of them. Gas giants larger than Jupiter, rocky planets similar to Earth, worlds orbiting multiple stars, planets with years lasting only a few days, planets where temperatures could melt metal, entire families of worlds unlike anything found in our own solar system. The universe turned out to be far more creative than anyone expected. Yet among all these discoveries, one category became especially important: potentially habitable planets, worlds located within what astronomers call the habitable zone. Sometimes this region is nicknamed the Goldilocks zone. Not too hot, not too cold, just right. In this narrow region around a star, liquid water may be able to exist on a planet's surface. And wherever liquid water exists, scientists become interested. Not because water automatically means life, but because every known form of life depends on it. Water is chemistry's playground. It allows molecules to interact. It transports nutrients. It regulates temperatures. On Earth, life appears almost everywhere liquid water can be found. Deep underground, inside glaciers, near volcanic vents, even within some of the harshest environments imaginable. So naturally, when astronomers search for life elsewhere, water becomes one of the first things they look for. At first glance, this might seem like an impossible task. After all, there are hundreds of billions of stars in the Milky Way alone. Where do you even begin? Surprisingly, the answer may lie with some of the smallest stars in the galaxy, red dwarfs. These stars are easy to overlook. They are smaller than our Sun, cooler than our Sun, dimmer than our Sun, yet they dominate the galaxy. Roughly 80% of all stars in the Milky Way are believed to be red dwarfs. That means when you look into the night sky, most stars actually belong to this category, even if many are too faint to see. Their small size creates a huge advantage for planet hunters. Around a star like our Sun, the habitable zone lies relatively far away. Planets take months or years to complete their orbits. This means astronomers must wait longer to collect enough observations. Red dwarfs are different. Because they are cooler, their habitable zones sit much closer to the star. Planets orbit quickly. Transits occur more frequently. Opportunities for detection increase dramatically. Suddenly, the search becomes far more manageable. And this is where things start getting exciting. Many planets discovered around red dwarfs are surprisingly Earth-sized. Some appear rocky. Others may contain vast amounts of water. Certain estimates suggest that some of these worlds could possess far more water than Earth itself. Entire global oceans, endless seas stretching beyond every horizon, planets where dry land may barely exist. For scientists searching for life, these discoveries are irresistible because every new planet represents a possibility, not a certainty, but a possibility, a chance that somewhere beyond our solar system, biology found another foothold, a chance that evolution played out differently beneath another sky, a chance that Earth is not unique. And among all these distant worlds, one has captured more attention than almost any other. Proxima b. Orbiting the closest star to our solar system, Proxima b sits just over 4 light-years away. In cosmic terms, that is practically next door. If humanity ever sends an interstellar probe beyond our solar system, there's a good chance this world will be one of its first destinations. From a distance, Proxima b appears promising. It resides within its star's habitable zone. It is roughly Earth-sized, and depending on its atmosphere and composition, liquid water may exist there. Yet the closer scientists look, the stranger the picture becomes, because being inside the habitable zone does not guarantee comfort. It does not guarantee oceans. It does not guarantee life. And it certainly does not guarantee a world that looks anything like Earth. In fact, Proxima b may belong to one of the strangest classes of planets ever imagined, a type of world where one side experiences eternal daylight, the other side experiences eternal night, a world where oceans may exist beneath a permanently fixed sun, a world that resembles a gigantic eye staring endlessly into space. And if these bizarre worlds truly exist, they may be far more common than anyone once believed, which raises a fascinating possibility. Perhaps the first alien world humanity visits will not look like Earth at all. Perhaps it will be looking back at us. Imagine standing on a beach beneath a sky where the sun never moves. Not because the day is unusually long, not because the planet rotates slowly, because the sun is permanently fixed in the same position forever, every hour, every day, every year. The same star hanging motionless above the horizon. No sunrise, no sunset, no seasons as we know them, no changing sky, no night, at least not where you are standing. Now imagine traveling across this world. As you move farther from the eternal daylight, the star slowly sinks lower in the sky. The air becomes colder, the oceans begin to freeze, shadows stretch farther across the landscape. Eventually, the star reaches the horizon and never rises again. Beyond that point lies endless darkness, a hemisphere locked in perpetual night, a frozen wilderness where temperatures plunge lower and lower the farther you travel from the boundary between light and dark. This strange world may sound like science fiction, yet astronomers believe planets like this could be surprisingly common throughout the galaxy. They are known as eyeball planets, and some of them may be among the most promising places to search for extraterrestrial life. The reason these worlds exist comes down to a process called tidal locking. Gravity is not just responsible for keeping planets in orbit. Over long periods of time, it can also alter how they rotate. The Moon provides a perfect example. It takes roughly the same amount of time for the Moon to rotate once on its axis as it takes to orbit Earth. As a result, The same side of the moon always faces us. For billions of years, humanity saw only one lunar face. The far side remained completely unknown until the space age finally revealed it. The same process can occur between stars and planets. In fact, it becomes even more likely when planets orbit very close to their stars. And as we learned in the previous chapter, many potentially habitable planets orbit red dwarfs. Because red dwarfs are cool stars, their habitable zones sit extremely close to them. Close enough that tidal locking becomes almost inevitable. Over millions or billions of years, the star's gravity gradually slows the planet's rotation until eventually one hemisphere always faces the star. The world becomes frozen in position, one side locked in eternal day, the other trapped in eternal night. At first glance, this sounds terrible for life. How could anything survive on a planet like that? The day side seems destined to become an overheated wasteland. The night side appears doomed to freeze solid. Yet reality may be far more interesting. Imagine an eyeball planet covered largely by water. The region directly beneath the star would receive constant energy. There, liquid oceans could exist, perhaps even vast ones. Viewed from space, this bright circular ocean would stand out against the surrounding ice like the iris of a giant eye. Hence the name. The farther away you travel from the center of illumination, the colder conditions become. Eventually, the ocean transitions into ice fields stretching toward the dark hemisphere. From orbit, the entire planet might genuinely resemble a gigantic eyeball staring toward its parent star. One bright central ocean, a frozen outer ring, and beyond that, endless darkness. What makes these worlds fascinating is that the boundary between day and night may be surprisingly comfortable. Scientists call this region the terminator zone. It is the narrow band separating perpetual sunlight from perpetual darkness. Temperatures here may be moderate. Water may remain liquid. Weather systems may circulate heat around the planet. And if life exists, this zone could become its preferred habitat. Imagine a civilization living beneath a sky where the sun permanently rests on the horizon, never rising, never setting, just hovering there eternally. Their entire concept of time would differ from ours. Their mythology would differ. Their calendars would differ. Perhaps they would not even understand the concepts of day and night. To them, the sky would simply be. The possibility becomes even more intriguing when we look at specific worlds. One of the most famous candidates is Proxima b, the same nearby planet we mentioned earlier. Located just over 4 light-years away, Proxima b likely experiences tidal locking due to its close orbit around its red dwarf star. If it possesses an atmosphere, things become especially interesting. Atmospheres act as giant heat transport systems. On Earth, winds and oceans constantly move energy around the globe. Warm air rises, cold air sinks, ocean currents redistribute heat across continents. Similar processes could occur on Proxima b. A thick atmosphere might carry heat from the day side toward the night side, preventing either hemisphere from becoming too extreme. The result could be a surprisingly stable climate, not Earth-like, but potentially habitable. Of course, there are challenges. Many scientists worry about a process called global freeze-over. Imagine sea ice forming on the dark side of the planet. Over time, that ice drifts toward warmer regions. More water freezes, more ice spreads. Eventually, the process could consume much of the planet's oceans. The world becomes a giant snowball, a frozen monument orbiting its star. Yet the opposite possibility also exists. Strong atmospheric circulation could maintain liquid oceans. Greenhouse gases such as carbon dioxide might trap enough heat to keep water from freezing completely. In that scenario, eyeball planets become some of the most attractive locations in the search for life. What makes this uncertainty exciting is that we genuinely do not know which outcome is more common. Some eyeball worlds may be frozen wastelands. Others may contain vast oceans. Some may have thick atmospheres. Others may have lost theirs long ago. The universe is likely producing every variation imaginable, and this reveals something important about planetary science. For most of history, humanity knew only one example of a habitable world, Earth. We naturally assumed other life-supporting planets would resemble it. Now we are beginning to realize that nature may have countless ways of creating environments suitable for life. The universe rarely copies itself. It improvises, again and again. Eyeball planets are one example. Ocean worlds are another. Super-Earths represent yet another category entirely. Some may contain more water than Earth ever possessed. Others may hide beneath dense atmospheres unlike anything in our solar system. The farther we look, the stranger planetary diversity becomes. And that diversity raises a remarkable possibility. Perhaps the worlds most capable of supporting life are not Earth-like at all. Perhaps the universe has been creating habitable environments we never imagined. Worlds covered by endless oceans. Worlds wrapped in permanent clouds. Worlds larger than Earth yet smaller than Neptune. Entire categories of planets absent from our own solar system. And among them may lie some of the most extraordinary places in the galaxy. The possibility of eyeball planets forces us to confront an uncomfortable realization. For most of human history, we assumed that if life existed elsewhere, it would probably emerge on a world that looked broadly similar to our own. A blue planet, white clouds, oceans and continents, familiar cycles of day and night. It was a reasonable assumption because Earth was the only example we had. Yet every year, as astronomers discover more planets orbiting distant stars, that assumption becomes harder to defend. Nature seems to have little interest in recreating the solar system. Instead, it keeps producing worlds that nobody expected. This shift in perspective may ultimately become one of the most important discoveries in astronomy. The search for life is no longer a search for another Earth. It is becoming a search for habitability in all its possible forms. And the more we look, the more diverse those forms appear to be. Many of the first exoplanets discovered were giant worlds larger than Jupiter orbiting impossibly close to their stars. These planets challenged existing theories almost immediately. According to the models astronomers had developed from studying our own solar system, giant planets were supposed to form far from their stars, where temperatures were low enough for large amounts of gas to accumulate. Yet here were enormous worlds circling their suns in a matter of days. Some were so close that their atmospheres were literally being stripped away by stellar radiation. Entire layers of gas were escaping into space, forming gigantic comet-like tails stretching millions of miles behind them. At first, researchers assumed these planets were rare exceptions. They weren't. The universe kept producing them. Then came another surprise. Scientists began finding planets larger than Earth but smaller than Neptune. This category hardly exists in our own solar system, yet it appears to be one of the most common types of planet in the galaxy. Some of these so-called super-Earths may possess thick atmospheres and rocky surfaces. Others may be covered entirely by oceans hundreds of miles deep. Entire classes of worlds that do not exist around our sun seem to be common elsewhere. Imagine standing on a planet where there are no continents at all, no mountains, no deserts, no forests, just water, endless water, an ocean stretching from horizon to horizon in every direction. Beneath you, the sea continues downward for unimaginable distances. On Earth, the deepest point in the Pacific Ocean reaches roughly 7 miles below sea level. On some of these ocean worlds, the water may extend hundreds of miles downward before reaching high-pressure ice. The pressures at those depths would be unlike anything naturally found on our planet. What kind of life could evolve in such an environment? The honest answer is that nobody knows. And that uncertainty is precisely what makes these worlds so fascinating. For centuries, discussions about alien life were mostly philosophical. Today, they are becoming scientific. Telescopes are beginning to examine planetary atmospheres directly. Researchers are searching for chemical signatures associated with biological activity. Every new discovery expands the range of environments that might potentially support life. What makes this especially exciting is that life on Earth has repeatedly demonstrated an astonishing ability to adapt. Microorganisms thrive in boiling hot springs. Others survive inside Antarctic ice. Some flourish near deep-sea hydrothermal vents where sunlight never reaches. If life can adapt to such extremes here, perhaps it can emerge under conditions that seem strange to us elsewhere. And the universe provides no shortage of strange conditions. Some planets orbit multiple stars. Imagine looking into the sky and seeing two suns. Shadows would split across the landscape. Daylight would change depending on the positions of both stars. In other systems, planets follow highly elliptical orbits. Their climates may swing dramatically over the course of a year. A world could spend part of its orbit frozen beneath global ice before moving closer to its star and briefly warming again. Then there are rogue planets. These objects may be among the loneliest worlds in existence. Unlike Earth, Mars, or Jupiter, rogue planets do not orbit stars at all. At some point in their history, gravitational interactions ejected them from their planetary systems. They now wander through interstellar space, alone, drifting between the stars in complete darkness. At first glance, they seem entirely inhospitable. Without a star, surface temperatures would plummet, sunlight would vanish. The world would become a frozen sphere moving silently through the galaxy. Yet even here, scientists hesitate to rule out the possibility of life. A sufficiently large rogue planet could retain internal heat generated by radioactive decay. Thick layers of ice might insulate underground oceans. Deep beneath the frozen surface, liquid water could persist for billions of years. The idea sounds incredible. An ocean hidden beneath a frozen shell, drifting through the darkness between stars. No sunrise, no sunset, no parent sun, just an isolated world carrying a secret sea through interstellar space. The more astronomers study exoplanets, the more they discover that reality consistently exceeds imagination. Worlds of lava, worlds of endless oceans, worlds trapped in eternal daylight, worlds wandering alone through the galaxy. Every time we think we have identified the limits of planetary diversity, nature quietly produces something even stranger. And perhaps the most remarkable part is that we have only just begun looking. The Milky Way contains hundreds of billions of stars. Most of them likely host planets. The number of worlds in our galaxy alone may exceed the number of humans who have ever lived. Yet we have studied only a tiny fraction of them. We are still in the earliest moments of planetary exploration. Future telescopes may reveal continents on distant worlds. They may detect weather systems. They may identify oceans, seasons, or even biosignatures. Entire categories of planets that remain unknown today may eventually become familiar. But as our understanding of real planets expanded, something unexpected happened. We began realizing that many of the worlds we once imagined were often just as fascinating as the worlds we discovered. Long before telescopes revealed exoplanets, astronomers spent centuries searching for planets that did not actually exist. Hidden worlds, missing worlds. planets invented to explain mysteries in the sky. Some of these searches led to important discoveries. Others became cautionary tales, and one of them inspired a planet so famous that it eventually found its way into science fiction itself, a world called Vulcan. The idea of Vulcan feels almost inevitable when you think about it. For thousands of years, every new improvement in astronomy seemed to reveal another hidden world. First came Mercury, Venus, Mars, Jupiter, and Saturn, the planets visible to the naked eye. Then telescopes improved. Astronomers began seeing farther. The solar system grew larger. Uranus was discovered. Later, Neptune emerged from mathematical predictions before anyone had actually seen it through a telescope. It was a triumph unlike anything astronomy had experienced before. Imagine what that must have felt like. A scientist notices that a distant planet isn't moving exactly as expected. Tiny deviations appear in its orbit, nothing dramatic, just enough to suggest that something unseen is exerting a gravitational pull. Mathematicians calculate where the invisible object should be. Telescopes point toward the predicted location, and there it is, an entirely new planet waiting in the darkness. Neptune's discovery was so successful that it changed the way astronomers thought. Suddenly, hidden planets seemed to be everywhere. If one invisible world could explain strange observations, why not another? This mindset would eventually lead scientists toward one of the most fascinating dead ends in astronomical history. The mystery began with Mercury. Of all the planets orbiting the Sun, Mercury behaves in a slightly unusual way. Its orbit is not perfectly stable. The point where Mercury comes closest to the Sun shifts over time. Today, this behavior is well understood, but during the 19th century, it became one of astronomy's greatest puzzles. Among those trying to solve it was the brilliant French mathematician Urbain Le Verrier, the same scientist whose calculations had helped predict Neptune. If mathematics had successfully revealed one hidden planet, perhaps it could reveal another. Le Verrier proposed a simple explanation. Maybe there was a planet closer to the Sun than Mercury, a world hidden in the Sun's overwhelming glare, a planet so difficult to observe that astronomers had simply missed it. He even gave it a name, Vulcan, named after the Roman god of fire. The name was perfect. If such a planet existed, it would orbit closer to the Sun than anything else in the solar system. Temperatures there would be extraordinary. The world would spend its entire existence immersed in intense solar radiation. Astronomers became fascinated. Reports began appearing from observers who believed they had seen Vulcan crossing the face of the Sun. Others claimed to spot it during solar eclipses. Excitement grew. Articles were written. Calculations multiplied. The search intensified. And yet something strange kept happening. Nobody could confirm it. One astronomer would report seeing Vulcan. Another would fail to find it. Predictions disagreed. Observations conflicted. Years passed. Then decades. The evidence remained frustratingly uncertain. The problem was not that scientists were foolish. In many ways, their reasoning was entirely logical. They were attempting to explain a real phenomenon using the best tools available at the time. Mercury's orbit genuinely behaved differently than expected. The mystery was real. The explanation was not. The solution arrived from a completely different direction. At the beginning of the 20th century, a relatively unknown physicist named Albert Einstein was developing an entirely new way of understanding gravity. For centuries, gravity had been viewed as a force acting between objects. Einstein proposed something far stranger. According to his theory of general relativity, gravity was not really a force at all. Massive objects distort the fabric of space-time itself. Planets move through those distortions, following paths created by the geometry of the universe. It sounded radical. At first, many scientists were skeptical. Then Einstein applied his equations to Mercury. The results were astonishing. Without adding a hidden planet, without inventing new objects, without changing any observations, his theory perfectly explained Mercury's strange orbit. Vulcan was no longer needed. A planet that had occupied scientific discussions for decades simply vanished, not because it had been destroyed, not because it escaped detection, because it never existed. In a way, Vulcan's story is beautiful. Science is often portrayed as a collection of facts, but it is really a process of correction. Ideas compete, evidence accumulates. Some explanations survive, others disappear. The goal is not to be right from the beginning. The goal is to move closer to reality. And sometimes reality turns out to be stranger than imagination. The irony is that while Vulcan disappeared, the search for hidden planets never truly ended. Even today, astronomers continue hunting for objects that may be lurking beyond the known boundaries of the solar system. This time, however, the evidence is more compelling. Far beyond Neptune lies a region known as the Kuiper Belt. It is a vast collection of icy bodies, dwarf planets, and frozen remnants left over from the formation of the solar system. Most of these objects follow predictable paths around the Sun, but a handful behave strangely. Their orbits appear clustered, almost as though something massive is influencing them, something unseen, something distant. This observation gave rise to a modern mystery known as Planet 9. Unlike Vulcan, Planet 9 has not been invented to explain a tiny discrepancy in a single orbit. Instead, it emerges from patterns observed across multiple distant objects. Computer simulations suggest that a planet perhaps 10 times more massive than Earth could explain what astronomers see. If it exists, Planet 9 would be an extraordinary world, far larger than Earth, far beyond Neptune. A year there could last tens of thousands of Earth years. Its orbit would carry it through some of the darkest and most remote regions of the solar system. At such distances, sunlight becomes little more than a bright star. The sun itself would barely illuminate the landscape. Yet despite years of searching, nobody has found it. Not yet. And so the story continues. Unlike Vulcan, Planet 9 remains a genuine possibility. Telescopes are still scanning the outer solar system. Researchers continue refining their models. Somewhere out there, a hidden giant may still be waiting. Of course, not every hidden planet story has been grounded in science. As astronomy became more popular, mysterious worlds began appearing in books, television programs, and internet rumors. Names like Nibiru captured public imagination. Entire predictions were built around invisible planets supposedly heading toward Earth. The problem was simple. The evidence never existed. A planet large enough to threaten Earth would be impossible to hide. Its gravity would disturb other planets. Its brightness would make it visible. Its effects would appear everywhere in astronomical observations. Reality once again proved less dramatic than speculation. Yet the popularity of such stories reveals something important about human nature. We love hidden worlds. We always have. Perhaps because every generation hopes there is still something waiting to be discovered. And history suggests that hope is often justified. Again and again, astronomy has expanded our understanding of reality by revealing worlds we never knew existed. The difference is that real discoveries tend to be even more interesting than fictional ones, because while scientists searched for hidden planets, they were also uncovering something equally remarkable: a deeper understanding of how planets themselves form, why they become round, why gravity shapes them the way it does, and why, despite all the strange worlds we have discovered, there are certain rules that almost every planet in the universe seems unable to escape. The possibility of hidden worlds like Planet 9 naturally raises another question. what would happen if we actually found it. Not just another planet, not another icy giant, but something truly different. A square planet, a triangular world, a giant cube drifting through space. At first glance, it seems like a ridiculous idea. After all, every planet we have ever observed appears roughly spherical. Earth is round, Mars is round, Jupiter is round. Even distant exoplanets seem to follow the same pattern. No matter where we look, nature keeps building planets in essentially the same shape. It almost feels suspicious. The universe contains astonishing diversity. Stars vary enormously in size and temperature. Galaxies come in countless forms. Planetary systems seem wildly different from one another. Yet planets themselves remain stubbornly similar, round again and again. The reason lies in one of the most powerful forces in existence, gravity. To understand why, we need to travel back billions of years to a time before planets existed at all. Every planet begins as chaos, not orderly continents, not mountains, not oceans, just enormous clouds of gas and dust drifting through space. These molecular clouds are the raw material of future solar systems. They contain hydrogen, helium, carbon, oxygen, silicon, iron, and countless other ingredients forged by earlier generations of stars. In many ways, they resemble cosmic recycling centers. The remains of ancient stars become the building blocks of future worlds. Eventually, something disturbs the cloud. Perhaps a nearby supernova explodes. Perhaps gravity slowly amplifies tiny density variations. Whatever the trigger, parts of the cloud begin collapsing inward. The material starts gathering together. As it falls, something important happens. The cloud begins spinning. Even a tiny amount of initial rotation becomes amplified as the cloud shrinks. The same principle explains why figure skaters spin faster when they pull their arms inward. Conservation of angular momentum takes over. The cloud flattens. A disk forms. At the center, a newborn star begins taking shape. Around it, countless particles collide. Dust grains stick together. Pebbles become rocks. Rocks become boulders. Boulders become planetesimals. The process sounds gentle. It is anything but. Early planetary systems are violent places. Objects constantly collide. Some shatter, others merge. Entire worlds are destroyed before they fully form. Yet over millions of years, larger and larger bodies emerge from the chaos. Gravity grows stronger. The future planets begin clearing out their neighborhoods. And eventually, something remarkable occurs. The growing planet becomes massive enough that gravity starts shaping the object itself. Every piece of material feels a pull toward the center. Not just some of it, all of it. Mountains collapse, valleys fill, irregularities smooth out. Gravity acts equally in every direction, constantly trying to bring matter closer to the center of mass. And there is only one shape that allows every point on the surface to sit as close to the center as possible. A sphere. The universe does not choose spheres because they are beautiful. It chooses them because they are efficient. Given enough mass, a planet has almost no choice. Gravity wins, always. This balance between gravity pulling inward and material resisting compression creates something scientists call hydrostatic equilibrium. The name sounds intimidating, but the concept is simple. Gravity pushes inward, internal pressure pushes outward. Eventually they reach a compromise. The planet stabilizes. Roundness emerges naturally. It is one of the most elegant examples of order appearing from chaos. Yet planets are not perfectly spherical. Far from it. Rotation complicates the picture. Imagine spinning a ball of soft clay. As it rotates, material begins moving outward near the equator. The faster it spins, the stronger this effect becomes. Gravity still tries to keep everything compact, but rotation pushes back. The result is a subtle bulge. Earth experiences this effect. Jupiter experiences it even more dramatically. Saturn takes it to another level entirely. These giant planets rotate so quickly that they become visibly flattened at their poles and wider around their equators. From a distance, they almost resemble slightly squashed spheres. Gravity still dominates, but rotation leaves its signature, a reminder that even seemingly simple shapes contain hidden complexity. This realization leads to an intriguing thought. If gravity works so hard to create spheres, what would happen if somehow it failed? What would life be like on a truly angular world? Imagine a planet shaped like a giant cube, not a slightly irregular sphere, a perfect cube. At first, it sounds amusing. Then you begin thinking about gravity, and everything becomes very strange, because gravity would no longer pull evenly across the surface. Standing in the center of one face would feel relatively normal, but as you walk toward an edge, the direction of gravity would begin changing. You would feel yourself pulled back toward the center. The terrain would effectively become steeper and steeper. The edges would resemble gigantic mountain ranges. The corners would become almost inaccessible. Water would flow away from them. Atmospheres would thin. Entire regions could become barren simply because gravity behaves differently there. A cube-shaped world would not merely look different, it would feel different. The very concept of geography would change. And as bizarre as that sounds, a triangular planet would be stranger still. Because once gravity loses its favorite shape, reality quickly becomes far more complicated than anyone expects. The moment we abandon the comfortable simplicity of spherical planets, the universe starts behaving in ways that feel almost dreamlike. A cube-shaped planet sounds strange enough. Yet even a cube still possesses broad, relatively flat surfaces, where life might adapt. A triangular world pushes things much further. On such a planet, gravity would create an environment unlike anything found anywhere in the known universe. To understand why, imagine standing near the center of one face. Gravity would pull you inward much as it does on Earth. The landscape might initially appear normal. Rivers could flow, lakes could form, atmospheres could gather. Life, at least in theory, might survive. But the farther you travel from the center, the more reality begins to change. The ground would seem to tilt beneath your feet, not because the planet itself is moving, because gravity is constantly trying to drag everything back toward the nearest center of mass. On Earth, we barely think about gravity because it behaves predictably. No matter where you stand, down points toward the center of the planet. On a triangular world, that simplicity disappears. The farther you move toward an edge, the stranger the pull becomes. Water would struggle to remain there. Air would drift away. Entire landscapes would slowly lose the resources needed to support life. Eventually, reaching an edge might feel like climbing the side of a colossal mountain. The terrain would become increasingly steep. Rivers would avoid these regions. Oceans would retreat from them. Atmospheres would thin dramatically. Life would cluster near gravitational lowlands, while vast portions of the world became barren. The most habitable regions might occupy only a small fraction of the planet's total surface. And yet gravity would not be the only problem. Climate would become equally bizarre. On Earth, sunlight curves smoothly across a spherical surface. The amount of energy received gradually changes with latitude. This creates familiar climate zones, tropical regions near the equator, temperate zones farther away, polar regions near the poles. The system is elegant, predictable, stable. Angular planets break that stability. Imagine a cube rotating through space. Depending on its orientation, entire faces might spend long periods receiving direct sunlight, while others receive very little. Some regions would become blisteringly hot. Others could remain locked in deep freezes. The transitions between climates might be abrupt rather than gradual. Crossing from one region to another could feel like traveling between different planets. A single journey might take you from desert-like heat to polar conditions within a surprisingly short distance. A triangular planet would create even more extreme contrast. One face might receive sunlight at favorable angles, while another receives it only indirectly. Temperatures could vary enormously across relatively small distances. Entire weather systems would behave differently. Winds would accelerate unpredictably as they move between regions of different atmospheric pressure. Even the concept of seasons could become distorted. Life evolving on such a world would experience an environment fundamentally different from anything humans have ever known. And then there is the atmosphere itself. Earth's atmosphere works because gravity distributes it relatively evenly around the planet. Air molecules constantly move, but they remain trapped by Earth's gravitational pull. The result is a stable blanket of gas protecting life from radiation, regulating temperatures, and supporting weather. On an angular world, this balance becomes unstable. Air would naturally accumulate in regions where gravity is strongest. Atmospheric pressure could vary dramatically from one location to another. Some areas might possess thick, breathable atmospheres. Others could resemble high-altitude mountain peaks, where breathing becomes difficult or impossible. Entire civilizations might be forced to develop only within specific gravitational basins. The corners and edges of the planet could become hostile frontiers. Beautiful, perhaps, but dangerous. It is fascinating to imagine how intelligent life might adapt. Would maps even resemble ours? Would oceans connect different regions or remain isolated within separate gravitational basins? Would cultures develop independently on different faces of the planet, separated by nearly impassable edges? A cube-shaped Earth could contain 6 enormous worlds sharing a single planet, and a triangular world might feel even more fragmented. Yet the deeper lesson hidden inside this thought experiment has very little to do with cubes or triangles. It reveals just how special gravity really is. Most of the stability we take for granted comes from gravity's relentless preference for spheres. Round planets create predictable climates, predictable oceans, predictable atmospheres. The spherical shape allows complexity to flourish because it minimizes chaos. In a sense, life may owe part of its existence to geometry. If planets commonly formed as cubes or pyramids, stable environments could be far rarer than they are. Gravity quietly creates order, and throughout the universe, order creates opportunity. Perhaps that is why nature keeps returning to spheres. Not because other shapes are impossible to imagine, but because spheres work, again and again. Yet even among spherical worlds, the universe still finds ways to surprise us. Some planets orbit so close to their stars that their atmospheres begin evaporating into space. Others are heated to temperatures capable of melting rock. Entire categories of objects exist somewhere between planets and stars, occupying a strange middle ground where the rules become less clear. And among these strange worlds are some of the hottest objects ever discovered. Objects so extreme that they blur the line between planet, star, and something else entirely. The farther astronomers explore the universe, the more they discover that nature rarely respects the categories we create for it. Planets are supposed to be planets. Stars are supposed to be stars. The distinction seems obvious. Stars generate energy through nuclear fusion. Planets do not. One shines, the other reflects. One creates light, the other merely borrows it. Simple, at least until the universe starts producing objects that sit directly between those definitions. And that is exactly what it has done. As astronomers searched for increasingly strange worlds beyond the solar system, They encountered objects that refused to fit neatly into any category. They were too massive to be planets, yet not massive enough to become true stars. They occupied a strange middle ground, a kind of cosmic no man's land where familiar definitions began to break down. These objects became known as brown dwarfs. The name is slightly misleading because most brown dwarfs are not actually brown. Some glow deep red, others radiate faint shades of purple or magenta, if human eyes could perceive enough infrared light. What makes them special is not their color, but their identity, or rather, their lack of one. A brown dwarf forms much like a star. Gravity pulls a cloud of gas inward. Temperatures rise. Pressure increases. The object grows larger and larger, but somewhere along the way, the process stalls. The brown dwarf never accumulates enough mass to ignite sustained hydrogen fusion. It comes incredibly close, close enough to become scorching hot, close enough to glow, close enough to resemble a small star, yet not quite enough. The result is something trapped between two worlds, neither planet nor star, neither fully successful nor fully failed. A cosmic object caught forever in transition. Some brown dwarfs reach temperatures of thousands of degrees. Their atmospheres contain bizarre weather systems unlike anything found in our solar system. Clouds made of vaporized metals drift through their skies. Superheated winds race around the globe. Entire layers of atmosphere rise and fall as heat escapes from deep within. Imagine looking up into a sky where droplets of molten iron condense into clouds. Not metaphorically, literally. A world where temperatures become so extreme that rock behaves more like a liquid than a solid. The universe creates places like this, not occasionally, regularly. And brown dwarfs are only the beginning, because once we move from failed stars to successful stars, temperatures become truly difficult to comprehend. Our sun feels unimaginably hot from a human perspective. The surface temperature reaches roughly 5,500 degrees Celsius. At those temperatures, virtually every material we encounter in daily life would instantly vaporize. Steel would melt, concrete would disintegrate, entire cities would disappear. Yet on the cosmic scale, the sun is surprisingly ordinary. Scattered throughout the galaxy are stars vastly larger, hotter, and more violent. Among them is one of the most famous stellar monsters ever discovered, Eta Carinae. Located roughly 7,500 light-years from Earth, Eta Carinae is not a single star, but a stellar system dominated by one of the most massive stars known. This giant contains well over 100 times the mass of our Sun and radiates millions of times more energy. Trying to imagine such a star is almost impossible. If placed where our Sun currently sits, it would completely transform the solar system. The planets would not merely become hotter, they would cease to exist. Mercury would vanish. Venus would vanish. Earth would vanish. The entire inner solar system would be consumed. And yet even this description fails to capture how unstable Eta Carinae truly is. Massive stars live fast. Their immense gravity compresses their cores with extraordinary force, accelerating nuclear fusion. They burn through their fuel at astonishing rates. While our Sun will survive for roughly 10 billion years, stars like Eta Carinae live dramatically shorter lives. They spend their existence racing toward destruction. In the 19th century, Eta Carinae underwent an event known as the Great Eruption. During this period, it briefly became one of the brightest stars visible in Earth's sky despite being thousands of light-years away. The eruption released enormous quantities of matter into surrounding space. The resulting cloud still surrounds the system today. It is known as the Homunculus Nebula. And thanks to modern telescopes, including the James Webb Space Telescope, we can observe it in extraordinary detail. The images are breathtaking. Towering clouds of gas expand outward from the star like gigantic cosmic wings. Shock waves ripple through surrounding material. Layers of ejected matter reveal the violence hidden within the star itself. Yet what makes Eta Carinae truly fascinating is not what it has already done. It is what it will eventually do. Because stars of this size rarely die quietly. They explode. And when they do, they become some of the hottest objects in the known universe. For a brief moment, a dying star can release more energy than entire galaxies. Temperatures soar to unimaginable levels. Elements heavier than iron are forged. Matter and radiation interact in ways impossible to reproduce on Earth. The star spends millions of years building toward a final act that unfolds in mere seconds. And those few seconds can reshape entire regions of space. The iron in your blood, the gold in jewelry, the uranium deep within Earth's crust. Many of these elements owe their existence to stellar explosions. In a very real sense, supernovae helped create the material world around us. The universe destroys stars so that more complex things can emerge. It is one of the strangest patterns in cosmic history: creation through destruction, order through chaos, death giving rise to new possibilities. Yet even the temperatures inside supernovae are not the end of the story. Because when physicists ask what the hottest thing in the universe actually is, they are forced to venture beyond stars entirely, beyond planets, beyond galaxies, toward conditions so extreme that the laws of physics themselves begin to blur, toward energies that existed only briefly after the birth of the universe itself, toward a realm where temperature stops being a useful human concept and becomes something far stranger. The story of heat in the universe begins to feel increasingly strange the closer we approach the extremes. A brown dwarf can reach thousands of degrees. A massive star like Eta Carinae becomes far hotter still. A supernova briefly outshines entire galaxies. And yet none of these objects hold the record. Not even close. Because when physicists ask about the hottest temperature that can exist, they are no longer talking about stars. They are no longer talking about planets or galaxies. They are talking about conditions so extreme that the universe itself begins to resemble something entirely different. To understand why, we first need to think about what temperature actually is. Most people imagine temperature as a property of an object. A cup of coffee is hot. Ice is cold. A star is hotter than both. While that is true, temperature is really a measure of motion. The faster particles move, the hotter something becomes. At absolute zero, particles possess the minimum possible energy allowed by quantum mechanics. As energy increases, particles move faster and faster. Heat rises. Simple enough. But then an interesting question appears. If temperature can increase by adding more energy, is there a limit? Can something become infinitely hot? For a long time, nobody knew. Then modern physics arrived, and the answer became far stranger than expected. Imagine rewinding cosmic history. Not millions of years, not billions, all the way back to the very beginning. The universe is expanding today. Galaxies are moving apart. Space itself continues stretching in every direction. If we reverse that process mentally, everything becomes closer together. Temperatures rise, densities increase. Continue far enough and you arrive at an era unlike anything that exists today. Stars do not exist yet. Galaxies do not exist yet. Atoms do not exist yet. The universe becomes a sea of pure energy, a place where ordinary concepts begin to lose meaning. According to current models, the early universe experienced temperatures so high that matter behaved in ways impossible to reproduce under normal conditions. Protons and neutrons could not form. Atomic nuclei could not form. even the familiar distinction between matter and radiation became blurred. The cosmos existed as an incredibly dense, incredibly hot plasma, a state of existence utterly alien to anything humans encounter in daily life. Yet remarkably, scientists have managed to recreate tiny glimpses of these conditions, not in space, on Earth, inside particle accelerators. Facilities such as the Large Hadron Collider accelerate particles to extraordinary speeds before smashing them together. For brief fractions of a second, temperatures exceed those found inside stars. Matter melts into a state known as quark-gluon plasma. This substance is extraordinary. Under normal circumstances, quarks are permanently confined inside protons and neutrons. They never exist independently. Yet at sufficiently high temperatures, those familiar particles dissolve. The universe temporarily returns to a condition resembling its earliest moments. For an instant, researchers create a tiny piece of the young cosmos. Then it disappears. The temperatures involved are difficult to comprehend, trillions of degrees. Numbers so large, they quickly become abstract. And yet, even these experiments remain unimaginably cooler than the highest temperature physics allows. Because according to current theories, there exists an ultimate limit known as the Planck temperature, approximately 142 nonillion Kelvin. Written out, the number becomes almost absurd. It contains 32 digits, so many that the human brain struggles to distinguish it from infinity. At this temperature, our current understanding of physics effectively breaks down. General relativity begins failing. Quantum mechanics begins failing. The frameworks used to describe reality stop working together. We enter a region where nobody truly knows what happens. This is one reason physicists remain fascinated by the earliest moments after the Big Bang. Those conditions may hold clues toward a deeper theory capable of uniting gravity and quantum mechanics. A theory of everything. The phrase sounds ambitious, perhaps impossibly ambitious. Yet throughout history, science has repeatedly revealed deeper layers beneath reality. Ancient civilizations believed Earth occupied the center of creation. Then astronomy expanded the picture. The solar system replaced Earth. The galaxy replaced the solar system. The observable universe replaced the galaxy. Again and again, the horizon moved outward. Perhaps the same process will eventually occur with physics itself. Perhaps our current theories are merely stepping stones towards something larger. The Planck temperature marks a boundary beyond which our maps become incomplete, a reminder that even our best understanding has limits. And there is something strangely comforting about that. The universe still contains mysteries. No matter how powerful our telescopes become, no matter how advanced our equations become, there remain regions where certainty fades, frontiers where curiosity continues driving exploration. The James Webb Space Telescope represents one such frontier. It is revealing ancient galaxies, strange worlds, and stellar nurseries with unprecedented clarity. Yet every discovery seems to expose deeper questions hiding beneath the surface. Questions about origins, questions about complexity, questions about how the universe became what it is today. And perhaps nowhere are those questions more tangible than in one simple substance: water. Because after all the strange planets, hidden worlds, exploding stars, and unimaginable temperatures, we eventually return to something surprisingly familiar. A liquid covering most of our own planet, a substance so common on Earth that we rarely think about it. Yet the farther astronomers look, the more they realize that water may be one of the most important clues in the search for life. The question is no longer whether water exists beyond Earth. We already know it does. The real question is how much. And the answer may be far more astonishing than anyone once imagined. The search for life often sounds far more complicated than it really is. When astronomers point giant telescopes toward distant stars, analyze planetary atmospheres, and build sophisticated computer models, they are ultimately searching for one thing: water. Not because water guarantees life, but because every living thing we know depends on it. Water transports nutrients, regulates temperature, enables chemistry. On Earth, wherever liquid water exists, life seems determined to find a way. Microorganisms thrive inside Antarctic ice. Bacteria survive near volcanic vents deep beneath the ocean. Entire ecosystems flourish in places once thought completely uninhabitable. If life emerged so readily here, perhaps it can emerge elsewhere. And as our understanding of the solar system has improved, a surprising realization has emerged. Earth may not be unusual because it has water. Earth may be unusual because so much of its water exists on the surface. The farther we explore, the more watery worlds we seem to find. Some hide their oceans beneath ice. Others bury them underground. Some may contain more water than Earth has ever possessed. Entire oceans may exist in places that receive almost no sunlight at all. Take Europa, for example. At first glance, Europa appears rather unimpressive. From a distance, it resembles a frozen white ball orbiting Jupiter. Its surface is covered by a thick shell of ice, marked by long cracks stretching across the landscape. Temperatures there remain far below freezing. Sunlight is weak. Conditions seem hostile. Yet beneath that icy exterior lies one of the most intriguing environments in the solar system. Scientists believe Europa hides a global ocean, not a small one, not a few scattered lakes, an ocean that may contain more water than all of Earth's oceans combined. Imagine standing on Europa's frozen surface. Beneath your feet, perhaps 10 or 20 miles below the ice, stretches a dark, liquid ocean extending around the entire moon. No beaches, no islands, no continents, just a planetary-scale sea concealed beneath an enormous frozen roof. The existence of such an ocean seems impossible at first. Europa orbits far from the Sun. Temperatures should keep everything frozen solid. Yet Jupiter changes the equation. As Europa travels around the giant planet, Jupiter's immense gravity constantly squeezes and stretches the moon. The process is subtle, but relentless. Europa flexes ever so slightly during each orbit. That flexing creates friction. The friction creates heat, and that heat may be enough to maintain a liquid ocean beneath the ice. It is one of the strangest sources of warmth in the solar system. No sunlight, no atmospheric greenhouse effect, just gravity quietly kneading the moon from the inside. The result may be an environment capable of supporting life, not intelligent life. Probably not fish, not giant alien sea monsters lurking beneath the ice, at least not according to current evidence, but perhaps microorganisms, simple life, the kind of life that dominated Earth for billions of years before complex organisms ever appeared. And if life could emerge independently on Europa, the implications would be staggering, because it would suggest that biology is not unique to Earth. It would suggest that life emerges whenever conditions allow. And Europa is not alone. Farther out, orbiting Saturn, another moon presents an equally fascinating mystery: Enceladus. Compared to Europa, Enceladus is tiny. You could fit it comfortably inside the state of Arizona. Yet despite its modest size, it has become one of the most exciting places in planetary science. The reason became apparent when NASA's Cassini spacecraft flew past the moon. Astronomers expected a frozen world. Instead, they discovered giant plumes erupting from the surface. Water vapor, ice particles, organic compounds, entire geysers blasting material into space. It was as if the moon itself was announcing the existence of an underground ocean. Every eruption carried pieces of that hidden ocean into space where spacecraft could study them. Scientists were astonished. Here was a moon actively spraying samples of its interior into the solar system. No drilling required. No need to melt through miles of ice. Enceladus was effectively doing the work for us. Even more exciting, some of the chemicals detected within those plumes resembled ingredients associated with hydrothermal activity. On Earth, hydrothermal vents support thriving ecosystems deep beneath the ocean floor. Sunlight never reaches those environments. Life survives using chemistry instead. If similar conditions exist on Enceladus, then one of the key requirements for life may already be present. Again, nobody knows whether life exists there, but the possibility refuses to disappear. And the deeper we look, the more widespread these hidden oceans appear. Even Mars joins the story. Today, Mars seems dry and lifeless. Dust storms sweep across barren landscapes. Ancient craters dominate the terrain. Rivers no longer flow. Yet Mars was not always like this. Its surface preserves evidence of an entirely different past. Ancient river valleys snake across the landscape. Dried lake beds remain visible. Minerals formed in the presence of liquid water cover large regions. Everything points toward the same conclusion. Billions of years ago, Mars was wetter, much wetter. Perhaps oceans once covered portions of its surface. Perhaps rain fell from Martian skies. Perhaps rivers carved the valleys that still exist today. Something happened. The atmosphere thinned, the planet cooled. Most surface water disappeared. Yet even now, frozen reservoirs remain. Ice hides beneath the surface. Water vapor drifts through the atmosphere. The red planet may still possess significant quantities of water locked away underground. In many ways, Mars serves as a reminder that planets can change dramatically over time. Habitability is not permanent. Worlds evolve, oceans appear, oceans disappear, atmospheres grow, atmospheres vanish. The solar system is not a collection of static objects. It is a collection of stories, each world following its own path through cosmic history. And perhaps the strangest chapter of all belongs to a moon that replaces water entirely. A world where rivers flow, lakes exist, rain falls, clouds drift across the sky, yet none of it is made of water. A place called Titan. A world so alien that it forces us to rethink what an ocean can even be. And once we arrive there, the very idea of a habitable world begins to change yet again. Titan feels like the perfect place to end our journey through strange worlds because it reminds us of something we have encountered again and again throughout this story. The universe rarely does what we expect. At first glance, Titan almost looks familiar. It has rivers, lakes, seas, clouds, rainfall, weather systems, shorelines stretching across the landscape. If viewed from a great distance, it might appear surprisingly Earth-like. Yet everything about it is different. The temperatures are so cold that water behaves like rock. The rivers are not water. The lakes are not water. The rain is not water. Instead, Titan's entire weather cycle runs on methane and ethane, hydrocarbons, the same types of molecules associated with fuels here on Earth. Imagine standing on the shore of a vast alien sea. Waves roll toward the coastline. Clouds drift overhead. Rain falls in the distance. Yet none of it could sustain a single fish, plant, or human being. The liquids filling Titan's lakes would freeze us solid long before we could appreciate the view. And yet Titan remains one of the most fascinating worlds in the solar system. Because beneath all of that strangeness lies a profound realization. Nature keeps finding new ways to build worlds. Some hide oceans beneath ice. Some lock one side permanently toward their stars. Some wander through interstellar space alone. Some replace water with liquid methane. Again and again, reality proves more imaginative than our expectations. Which brings us back to a question that has quietly followed us throughout this entire journey. Why does Earth have so much water in the first place? The answer seems obvious, until you think about it. Our planet is covered by oceans. Water shapes climates. Water drives weather. Water makes life possible. It feels so natural that we rarely stop to ask where it came from. Yet, when scientists investigate Earth's origins, the situation becomes surprisingly complicated. The early solar system was not a friendly place for water. 4.5 billion years ago, the region where Earth formed was significantly hotter than it is today. Temperatures near the young sun were high enough that volatile substances struggled to survive. Water should have had difficulty condensing in large quantities so close to the sun. And yet somehow, Earth acquired enough water to cover more than 70% of its surface. Where did it come from? For decades, one popular idea suggested that meteorites delivered most of it. The concept was elegant. Icy bodies formed farther from the sun, where conditions were colder. Later, impacts transported that water inward. Earth became hydrated through countless collisions over millions of years. Simple, reasonable, perhaps even correct. Yet as scientists began studying ancient meteorites in greater detail, problems appeared. Some of the samples turned out to be surprisingly dry, far drier than expected. In fact, certain meteorites contained so little water that they seemed incapable of explaining Earth's vast oceans. Suddenly, the mystery returned. Perhaps meteorites delivered some water, but maybe not all of it. Alternative theories emerged. Some researchers proposed that hydrogen trapped deep within the young Earth combined with oxygen to form water over time. Others suggested that Earth accumulated water-rich material during its formation and somehow managed to retain it despite the extreme conditions of the early solar system. The truth may involve several processes working together, and that uncertainty reveals something remarkable. We still do not know exactly how Earth's oceans formed. Think about that for a moment. Humanity has mapped the moon, sent probes beyond the solar system, detected planets orbiting distant stars, observed galaxies billions of light years away. Yet the origin of the water covering our own world remains partly unresolved. There is something wonderfully humbling about that. The closer we look at reality, the more mysteries emerge. The same pattern appears throughout astronomy. We searched for planets and found entire categories of worlds we never imagined. We searched for life and discovered hidden oceans beneath frozen moons. We searched for the hottest objects in existence and found conditions resembling the first moments after the Big Bang. We searched for the origins of water and discovered that even Earth's story remains incomplete. Every answer opens another question. Every discovery reveals another horizon. Perhaps that is the real lesson hidden within all these strange worlds. The universe is not a collection of isolated objects. It is a continuous story. The oceans of Earth connect to the icy reservoirs of Mars. Mars connects to Europa. Europa connects to Enceladus. Enceladus connects to Titan. Titan connects to distant exoplanets orbiting red dwarfs. Those exoplanets connect to the stars that formed them. Those stars connect to earlier generations of stars that forged the elements themselves. Everything traces backward through an unbroken chain stretching to the birth of the universe. And somewhere along that chain, matter became oceans. Oceans became chemistry. Chemistry became life. Life became observers. Observers became curious. And curiosity built telescopes capable of exploring the cosmos that created them. That may be the strangest transformation of all. Not eyeball planets, not hidden oceans, not hypothetical worlds, but the fact that the universe eventually produced creatures capable of wondering about it. Creatures capable of standing beside an ocean on one small planet and asking where it came from. creatures capable of looking toward distant stars and imagining entirely new worlds. And as long as those questions remain unanswered, the journey continues. Because somewhere beyond the next discovery lies another mystery, another world, another ocean, another story waiting to be told. If you enjoyed this journey through the strangest worlds, hidden oceans, impossible planets, and cosmic mysteries of the universe, make sure to subscribe to Epic Space News. There are still countless worlds left to explore, and together we'll continue searching for the answers hidden among the stars. Until next time, keep looking up.